The information bottleneck is a method of lossy compression of relevant information. Suppose that we would like to extract from an input x its most informative bits about a label or reference variable y. That is, we seek a representation x hat of x that captures as much information about y as possible, subject to a constraint ix on input compression. Varying the constraint yields the IB curve, which describes the fundamental trade-off between input compression and the preservation of relevant information. The IB curve upper bounds the region of achievable representations in the information plane. By definition, points above it cannot be obtained, regardless of input encoding. Despite the IB's acceptance and applications, surprisingly few techniques exist to solve it numerically, even for finite problems whose distribution is known. Algorithms to date usually approximate a single curve point. Starting at a suboptimal initialization, they typically try to approach the curve on every iteration. However, they make little to no use of the cost invested in computing nearby points on the curve. A combination of several insights permits the novel algorithm. In a nutshell, we argue that IB solutions typically follow a piecewise smooth trajectory dictated by an ordinary differential equation, which we derive anew. The ODE is violated when solutions change qualitatively, at its bifurcations, or phase transitions. Combining these insights permits a surprisingly accurate algorithm whose basic idea is as follows. Observe that the curve's extreme points are particularly easy to obtain. No relevant information is preserved when the entire input is discarded. This trivial solution is achieved via the constant encoding. At the other extremity, when no input compression is required, then no relevant information is lost via the diagonal encoding. Between these extremities lie intermediate optimal representations. What if we could follow those as information is being compressed? That would allow us to reconstruct the entire curve by tracking a solution's path. Since points above the curve are unachievable, this is similar to walking along a cliff edge. However, this planar description is misleadingly simple since it conceals the dynamics underlying the IB curve. The representation achieving a point in the plane is described by a probability distribution P, which is merely a vector in some high-dimensional space. We argue that curve-achieving representations follow a piecewise real analytic trajectory dictated by the IB's ODE. Curve-achieving distributions are shown here as a function of a time-like variable, beta, which parameterizes the curve. The upper and bottom plots depict its coordinates. The trivial solution is marked by a blue vertical to the left, and the diagonal encoding to the right. These follow a real analytic trajectory as input information is being compressed. However, analyticity is broken where the solution changes qualitatively, at a bifurcation. The green and blue clusters here collide and merge into one at the red vertical. This example depicts the conceptually simple cluster merging bifurcation, one of several types. Therefore, to follow the curve, we not only detect IB bifurcations but also identify their type. This permits their proper handling. We provide several theoretical contributions to realize an ODE-based algorithm for the IB. Rewriting fixed points P of the IB equations as roots of a nonlinear operator allows us to consider the derivatives implied by f equals 0. We derive the IB ODE in a coordinate system that best suits our needs. Our approach to IB bifurcations is based on a reduction, removing redundant coordinates. To achieve these, we exploit two often overlooked properties of the IB. First, the IB's intimate relations with the theory of lossy data compression suggest a minimally sufficient coordinate system. This facilitates a clean treatment of IB bifurcations, which are either continuous or discontinuous in beta. Second, the real analyticity of the IB equations sheds light on its solution structure, implying that curve-achieving distributions are piecewise real analytic. Combined, these reveal subtle practical caveats that are important for its computation. Our results suggest that the IB is inherently infinite-dimensional, even for finite problems. To our understanding, this hindered the understanding of IB bifurcations throughout the years. The above enables our new surprisingly accurate numerical algorithm for the IB. Though, perhaps more importantly, the discussion of discontinuous bifurcations obliges one to take a hard look at what the IB truly is. Our algorithm yields surprisingly accurate results. Its approximate IB curves to the right are visually indistinguishable from the true curve, even on very few grid points.
Do you want to show your research progress to more scholars? Contribute an entry that will be linked to your paper on the encyclopedia platform, providing an opportunity for over 35,000 scholars to access and explore your research. Have you ever tried to show your latest research in a vivid way? Encyclopedia's SciPlayer provides a service with which you can transfer your research to a live video format. Do you want to publish a new paper? Encyclopedia has an international, peer-reviewed, and open-access journal. Do you require a discount when you publish research in journals? Anyone who contributes to Encyclopedia can obtain vouchers for MDPI Journal's article processing charges. Encyclopedia aims to create an open-access knowledge-sharing platform for all scholars. To find more information, search for encyclopedia.pub.